Okay, let's begin. So, in the last class, we looked at this method of current injection to estimate the nonlinearity in circuits. So, today we'll look at something called systematic mismatch, which could result in what is known as systematic offset. So, have you encountered the systematic offset earlier in this course? Somewhere there? Yeah, if you remember in the two-stage OTA, we told if you don't have the same current densities for all the PMOS, that results in a systematic offset, right? So basically, systematic mismatch or offset refers to anything that as a designer you could do to prevent. It's not something random. Okay, so this systematic mismatch could arise in schematic itself. One example is what you mentioned. It could be as simple as not having the same drain to source voltage in a current mirror, in which case the current mirroring will not be accurate. And after doing schematic, the job is not done. We have to do the layout, wherein you say physically how the transistors are placed and how the interconnections are made. And it turns out you can have a lot of systematic mismatches in layout. So today we look at some basics of analog layout. And for that, let me take a simple inverting amplifier as an example. So let's say this is my input, this is output. So say this is some 10K and this is some 20K. So we get a gain of 2. Now, of course, you know how we can find the dimensions of a resistor. So from the sheet resistance says what is the resistance per square. From this you can get the ratio, and from the mismatch information you get the area, and from that you can find what you want, right? And let's say you have put a resistor like this with some length and width 10K. Now we need to have a resistor of 20K, and one thing to do is to take the material with twice the length and same width, right? So do you foresee any issues with this, or this is fine? What do you mean by area? Yeah, I mean that we cannot prevent, right? Because the resistance is basically sheet resistance times L by W, right? So what I'm asking is, I mean, yeah, you need to have larger area, that's fine, but I want 10K and 20K. That is, this one must be twice this guy. See, I'm okay even if this changes slightly, but I should want the other resistor to be twice this. Okay, so let me help. See, note that the resistances will be made using some polysilicon or some diffusion, some material, and to make contacts you will have to put something called bias. Okay, and if you look at the side view, you'll have the P substrate, and then the diffusion is somewhere here, and say this is the polysilicon, and you'll have multiple metal layers like this. To make connections, we'll have to connect to a metal. So basically, we'll be putting some contacts or vias like this. Say from diffusion to poly.
Metal contacts.
Metal contacts. Basically, it is basically something that connects the two layers. That's all. Even between metals, you will have vias so that you can connect one metal layer to the other. Okay. So same will happen here also. We'll have them. Now, if you see the metal will be connected like this. Right, or maybe for dramatic effect I'll say it's like this. So now if you look at it, the charge flow is not uniform throughout the width of the material, right, because the charges are entering only in this portion. So basically in this part there is no resistance provided, right? So the charges enter till this part only in the small region. From here they might take the entire width and then they will reach here. So same will happen here also, right? So what you can do is you can basically split this entire resistance into 3 parts, at the corners and one at the middle. Okay. So the actual resistance you get is twice this corner one and the middle portion. So similarly you will have the same corner stuff, some 2 RC plus some R naught prime. So basically you see that the resistance doesn't scale exactly as a factor of 2. That's simply because you have this change in the basically the current flow is not uniform throughout the length, and also these vias that you put, they will have their own resistance. Okay, so this RC will include the resistance of that via also. So obviously you see the resistance doesn't scale. So what is one simple thing that you can do to get a ratioed resistor? That is, I mean, you see that if I do this, I can't get a resistance which is twice this guy.
Series combination.
Series combination meaning? Yeah, how do you do that?
R1 and R2 like series.
No, I want one 10k and I want a 20k resistor. I have put a 10k resistor. Now I want to get a resistor which is
Another two metal contacts in between.
2 metal contacts.
I have only one metal. Two 10k and then one metal contact connect.
Yeah, so I think I get what you see. What he's saying is you take, this is the 10k resistor, you can put 2 of them like this, right? And then let's say you put a via, and one thing about vias is you usually don't put a single via, you try to put at least 2. That's simply because putting multiple vias in parallel like this, that will reduce the contact resistance also. Plus it helps with reliability, because it is possible if you put a single via, there could be some defect in it, it might not make contact eventually. So now you do this and connect these two in series like this, right? So now this is guaranteed to have twice the resistance as this guy. If this is some R prime, this will be twice that. Okay. So, and also other thing is, say if you have some the first 10k resistor like this, you don't put the other two like this. Okay. Now here you see the current flow is happening vertically here. Here it happens horizontally. So there is some inherent mismatch in this. Okay. So you always try to keep the same orientation for devices that you want to be matched. So the 3 takeaways are, you keep the same orientation, and if you want to get something that is an integer multiple of, or integer fraction of some other width, you always put multiple devices and connect them in series or parallel. Don't use a single device with integer multiple or integer fraction width. Okay? So you basically replicate and connect, and also don't use single via. Okay. So now let us say I have this. So this is the 10k and this is the 220k. So I place them like this. So yeah, do you think all these 3 are identical, or do you see something else that is different for the 3 of them? No, assume that geometrically they are identical. Okay, geometrically they have identical shapes, there is no change in the shapes and structure, but just by looking at it, do you see something is different for the 3 of them? Okay, location is fine, but yeah, that is okay. Yeah, besides that,
surroundings.
Yeah, basically like he's saying, if you look at this guy, both to its left and right it sees a resistor, whereas this guy, it doesn't see anything on one of its sides. Same with this guy. Okay, and in on chip it turns out any property also depends on what is there in its surrounding for that particular material. Okay, of course it's a weak dependence, but if you want it to be matched properly, even the surroundings or the environment must be identical. So
How resistance will change with the surroundings?
no, basically here there will be some current flow here.
Like electric field and that one.
Some, I mean, there could be lots of effects. Okay. So what do you think is something that we can do to make the environment same?
We can't register the
No, I mean the problem is this guy sees two resistors on both of its sides, but this guy doesn't see a resistor this side, and this guy doesn't see anything this side. So what can we do?
keep two registers on this side.
Yeah.
Don't
So
use them.
yeah, the simple fix is this, right? You put two resistors on either sides here. But we don't use it. So these are called dummies. So they just exist to provide similar environment for all the elements that you have. Okay. And I mean, see, this is basically in layout, it's all based on logic and common sense. There is no lot of technicality involved, right? So just look at it and you see that the environment is different. So the logical thing to do is put identical stuff on either sides. So this of course is dummy, will not be used, so you can connect its input and output like this. So you always use dummies to match the environment. Okay. So now let's say we have this guy. So there is one other issue that can happen, which is this. So it turns out in the fabrication process, during every step, there is going to be some gradient. That is, let's say you dope. So the doping concentration might have some linear gradient like this along this axis, right? Similarly, let's say you have some circuit here operating, like burning a lot of current. The temperature in this part will be much hotter compared to the temperature this side. So even with respect to temperature, there could be some gradient. Okay. So, and if the gradient is linear, which is what we usually assume, then it turns out this resistance of all these guys will also not be same. So this could be some R, this could be some R plus delta R. It's a linear gradient, so the resistance values will also increase or decrease in a linear fashion. So now you see that my single resistor has a value R. The series combination has 2 times R plus 3 delta R. So the ratio is gone, right? So obviously this is not something that is good.
It is systematic error.
Yeah. So now what do you think we can do to get a ratioed resistor? That is, I want something with R0 and something with 2R0.
So do we know the gradients? Like how is this slope changing?
No, that's what we assume that it's linear.
I mean, slope we don't know.
We don't know the slope, but we know for a fact everything is linear. That is, if the first one is R, the other could be R plus delta R, the next one is R plus 2 delta R. The values of delta R is not known. And see, for me that doesn't matter also. I want something which has a resistance R0, another instance which has a resistance twice that. That's all I want. And we see that if I connect these two and call this as my 2R0, that is not working. So can you think of something by which I can get? Basically I have 3 instances. I'll have to connect 2 of them in series so that the effective series resistance is twice the other resistance.
Sir, I don't know, but there will be a resistor in left of R also. That will be R minus delta.
No, that doesn't matter, right? We are only interested in 3.
Means assume there will be something R minus delta, then put them in series.
I mean, okay. Huh? Yeah, I mean, what you're saying is that, but better solution is what she's saying. What she's saying, we can connect these 2 guys, right? That's also same as what you told, right? I mean, if okay, so this now becomes twice the resistance, which is 2R plus 2 delta R, whereas this is R plus delta R, right? So now this is my 2R0 and this is my R. Okay. So I mean, if you take one more example, let's say I want R and 4R, okay, R0 and 4R0. So basically have, let's say, 5 resistors like this, 3, 4 and 5. Again the same thing, this is R, say R plus delta R. So how will I choose the resistors here? 2, 3, 4, 5, yeah. I want to choose 4 of them and put them in series so that the effective resistance is 4 times the other resistance. So which one do you think I can choose as the single resistor?
R plus to the
So I can basically choose the middle guy as the single resistor or not,
and put R.
and basically connect these two guys. So this will be 4. Okay. And I mean, if you think about it, the logic is you try to keep the centroid for all the elements same, right? The common, I mean, all the elements have the same centroid. Okay. So this is called common centroid layout. Again, this is coming from plain logic and common sense, right? There is not a lot of technicality involved. So yeah, so if you do this common centroid layout, any variations or mismatch due to linear gradient, that completely gets cancelled. Okay. Now of course, if you similarly have say R and 8R, you can actually put like this. The middle one will be the R, and the 4 here on either sides, you connect them to get 8R. But here you see that the individual elements are physically placed far apart, and it logically makes sense that the closer the elements are, better they will be matched. So instead of putting them in 1D array, you can actually try to put them in a 2D array like this. So this way it becomes more compact, and again we try to do common centroid in both axes, that is in this axis and this axis, so that linear gradients in both directions can get cancelled. So if that is the case, which of the things I will choose as the R? The middle one. Okay, because this is the middle, I mean common center in both axes, right? So I'll choose this as the middle, and the other ones I'll have to connect. So basically I'll do something like this, I don't know, and the bottom things like this, something. Okay, basically I have to connect all the other 8 in series. Let's say, and of course you also put dummies, so that is crucial. So you put dummies on the sides.
How these are in series
basically? I mean, I didn't show the connection, but the connection might not be representative, but what I'm saying is you have to connect all of them in series. That's all. Okay, now it looks like put in parallel, right? But that's okay. You basically have to connect all of them. That's what I'm trying to say. Okay, but yeah, so the problem in doing common centroid is now you see that the routing becomes slightly complicated, right? So that is the price you have to pay. So basically 3 things you always do. First, you replicate stuff. If you want to get some dimension which is larger or smaller, you put smaller stuffs and like put them in series or parallel. Okay, so always replicate and connect in series or parallel to get larger or smaller dimensions. Always use dummies, and try to do common centroid if matching is really critical. Okay, and if you think about it, this guy basically comes for free. I mean, you're not losing anything, right? This is basically no penalties here. If you put dummies, you are spending some area, and common centroid routing becomes more complex. Right? So the first 2 we can always do. It's nothing. Common centroid, you do it if it's really required, because if you have a lot of devices, maybe connecting them might become very complicated. So it again depends on case by case basis. So that is about the resistors. So now let's come to our op amp. So again, even with respect to the MOS transistors, the same guidelines which I mentioned here holds good. Okay, and let's say we look at our tail transistor, and let's say it's biased using a current mirror like this. Okay. So this goes to outside where I provide the current. Let's say the ratio is some 1:20, or let's say it's now 1:2 for simplicity. So this diode connected MOS, let us say you have placed it. So this is the width, this is the length. So now I want to have a structure which is exactly twice this guy, right? So of course the one brute force way is to take a single device which has twice the width like this. Better thing to do is to put two of them and put them in parallel, right? If I call this as drain, this could be my source, this is source and drain. So I'll connect the sources, drains, and with respect to MOSFET, these are called multipliers. So here the number of multipliers is 2. And we can also do one other thing to get twice the width. That is, if you look here, we have two sources and we are basically connecting them, right? So instead I can just have a shared source junction for both of them, right? So that gives a much more compact structure which will look like this. So this is the drain, this is the shared source, and this is the drain. So now we can connect the drains and gates, and this is called fingered layout, because if you put multiple of them it apparently looks like fingers. And the advantage of this is that, see, now here you have basically two source junctions. So the parasitic capacitance or the parasitics at the source junction is much higher because you have two of them. Whereas by sharing them you are basically reducing the parasitic here. But when you want to have a case where I want to get a device which is twice this guy, it is better to use multipliers, because this literally is putting two devices in parallel, right? So this will replicate this multiplication by 2 more accurately. Okay, whereas here it might not be really accurate. But let's say when it comes to my input diff pair, so here let's say I calculate that my width is say some 12 micro by some 60 nano something. Now again, usually you don't put a single transistor which is 12 micrometer wide. Here you again either split it as multipliers or fingers, and here usually it's better to use fingers, because in the earlier case we had a transistor with a width W and we wanted to have twice it, so then it makes sense to put multiple of them in parallel. Here all I want is some transistor with the width 12 micron. So there I could as well use a finger to reduce the parasitics. So usually the total width will be the number of multipliers times the number of fingers times the finger width. Okay. You can basically have a combination of multipliers and fingers, right? And here I could choose my number of multiplier to be 1. And usually the finger width, you don't choose it beyond a few micrometers. That's because all the device models in practice are much more accurate for reasonable widths. If you choose a really small finger width or a really large finger width, the models will not be really accurate. So you let's say choose 1 micron, then I can have 12 fingers if this is 1 micro. Okay. And of course this 1 micro, again you can place it as in 1D array as 1:12, that is 12 of them in x-axis. But if you wanted to have compact, you can basically put, let's say, 4 fingers. I'll just write it like this. See, this is basically putting 12 fingers like this right? This basically, instead of making this, if you want it to be compact, you can basically say I'll have 4 fingers and then multiply it 3 times. That is this is 4 fingers and then I'll put 3 copies of them and connect. That will make it compact. Okay. And again here you'll have to put dummies, and for putting dummies, one thing you can do is instead of putting another device on either sides, I can add one more finger. Okay. So what I can do is this. I can put an additional finger on either sides like this. So if this is my source, this will be drain, source, drain, source, drain, source. Okay, now, I mean, the same thing you can also realize by having 4 multipliers with 3 fingers, right? This is also fine, but there is some minor thing with respect to using odd number of fingers. So maybe I'll draw it here. Let's say I do it here. I have 3 fingers and I'm going to put 4 of them, in the vertical direction. But here if you were to put dummies,
X, Y, and Z.
no. For us, we have only control in 2 planes. I mean, 1 plane, 2 axes. Okay. So let's say now you want to put a dummy, you will add additional finger here, right? But now if you see, this will be source, drain, source, drain, source, drain. If you use even number of fingers, you see that the device is more symmetric. You have source on either ends and here is the center. But if you use odd number of fingers, one is source and one is drain, it's not really symmetric. So that's one minor thing. You see if we can use even number of fingers. Of course, it's not a hard and fast rule. Okay. So that's about this, and finally let's look at something about metal connections. So again, as I mentioned, in all our processes we will have multiple metal layers, metal 1, metal 2 to say metal 10, and it's a good practice to say have all the routings in the horizontal directions in say odd metal layers and the vertical routings in even metal layers, or vice versa. Odd and even doesn't matter. And the reason is again really logical, because say if you have 2 blocks and I want to connect them, some connection I need to make, and let us say I do it in metal 1. Now remember that we will have some routings in this space. Now if I make sure that the routings that are happening in the vertical direction are done with even metal layers, so I'll have some things like this, but I'll be sure that this will be either in metal 4 or metal 6. I will be guaranteed that there will be no metal in the first metal layer running vertically. So that way you don't run the issue of sorry.
This ensures that 2 wires, 2 contacts don't go.
Yeah, basically, I mean, basically, if let us say if you don't follow it, you could have a possibility where one of the routings is also in metal 1. Then this will get shorted, right? So basically, you will have something like this and something like this, and how to draw 3D. That will get shorted, but that's not what you want. If you follow this thing, you can be assured that there will be no similar metal connections happening in the other dimension. So you can make all the connections without any worry.
So when we give a design to the foundry does this?
No, you have to do. Yeah, we have to do. That's why I'm saying this, right? Foundry never does it. See, foundry is just an automated thing. You say where the transistors are placed, how the metal connections are made. You do the layout, send it. It is all automated. Okay. So that is why I am explaining all this. See, and also let us say you have your diff amp. Say this is my positive negative inputs. You want to connect the inputs. So let us say this is the odd metals in the vertical direction, and my inputs are somewhere here. So one thing is to do this. I put say via and connect the 2 metals. Now you see that the 2 lines are not really same. The parastics will be different. So one thing that can be done is to extend the 2 lines so that they have the same length, so that the parastic capacitance will be same. Okay, but of course this will make sure that the resistance here is different, right? Because this will have, the top one will have a larger resistance. So if you are worried about the resistance, the one thing you can do is this. See, this is the plus and minus again. You can basically take them like this and then roll. So this way the lengths are really same. The only difference is this portion. That's very small. Again, this all again logic and common sense, right? See, in layout, all you need is logic and a bit of OCD, so that you make sure everything is fine. OCD, obsessive compulsive disorder. You want everything to be really aligned, matched. Okay. Yeah, so you do all these things and then finally the layout is ready, but again the things don't end there. After finishing the layout, you run what is called DRC, or a design rule check. This is basically, that is basically this. Basically the foundry will say there are some rules which has to be followed for me to fabricate. Some things like minimum distance between two metals, minimum width of anything.
That is in terms of lambda something like that.
Yeah, that is old style, but now it's all, yeah. And after making sure the design rules are passed, you have to run what is called LVS. That is similar. That is simply layout versus schematic. This is to make sure that whatever you have put in layout is same as what you have in schematic, right? And finally, we have to do what is known as a PEX, or a parasitic extraction. Okay. And that's simply because, say, in schematic, let us say you have this guy, a MOSFET resistor, you connect them, it's a nice shot, right? But in layout, you have the MOSFET placed here, the resistor is placed here, let us say. So we are going to put bias like this and then connect them using a metal. Now this metal is no longer a short, it will have its own parasitic resistance, capacitance. So you have to extract these parasitics, include in your schematic and run it, right?
Sir, how these parasitics are? These are parasitic. How can we calculate them?
If you know the exact, see, you know what kind of metals are being used.
The brute force method.
No, it's not a brute force. The foundry will give all the information. Basically, the foundry will know what is the metal. Let's say it's aluminium or something. So it knows the resistivity. From the layout, you know what is the width and length. So I can know what is the resistance, right? So, and similarly, from the foundry will know the vertical distance from the substrate to the metal. From this I can find what is the parasitic capacitance. So these you don't do. These are actually, all these things, we have specific rule files given from the foundry, and we have specific tools for running these things, and it will be done automatically. You don't have to sit and calculate.
Yes, sir.
Okay. So again, this parasitic extraction can be done in multiple, this one. So first is to just extract the parasitic capacitance. So that is only the parasitic capacitance from each metal routing to ground or the P substrate. Next is to extract the parasitic capacitance and what is known as coupling capacitance. That basically says, let's say you have some other connection in some metal layer here. Because of the overlap, there will be some coupling capacitance. Or you could have some other metal running like this. So now these two metal layers are parallel, you will have some coupling capacitance. So include all that and run. And third is to extract only the resistance. And the last is the final stuff where you include everything and run. And this is the ultimate simulation that you have to do, so that you include all parasitics, and with all these parasitics your circuit should work. Okay?
Sir, one basic question. We have never considered inductance in the.
Yeah, that is good point. Inductance also is there actually, but that at low frequencies it's not of a concern. If you go to say gigahertz of frequencies, then as you mentioned, even the inductance has to be extracted.
Inductance is offered by which how?
Every metal will do, right? Basically any metal will have. See, one thing here is, say I extract only the capacitances alone. Okay. So what I will be doing is, let us say this short, this from each of, from this net, I might have some parasitic capacitance to ground, say some coupling capacitance to this node and so on, right? And basically I'm not changing the number of nodes, the number of nodes is still the same, right? From that node I'm just estimating the capacitances to all the other nodes. But if I extract the parasitic resistance with the capacitance, this single shot, this will be modeled as a distributed RC network like this, just like in transmission lines. Okay, and the number of such RC elements depend on how long your routing is and so on. So basically what that means is, if you have long routings, which you might have in most cases, the number of nodes after you extract these parasitics will increase a lot. Earlier you just had one node here, that one node will explode to say 10 nodes, right? And if you have a big ADC or a PLL, it is very common to have a full parasitic extracted simulation running for several days. That's exactly why as a designer you should know what things are more critical in your design. And let us say you find that, if you know that, let us say in some particular net I can have more parasitic capacitance, there you can do little bit sloppy. But let us say you find that I can't tolerate any parasitic resistance in some path, then you do your layout accordingly. That's exactly why you should have some understanding of what the circuit is doing and what is more critical in your circuit. You cannot always rely on simulations, because the final simulations might run for several days. You can't change something and say if it's working or not. Okay? And I mean, let's say similarly you find, say, some net is there, output net in some metal. You don't want this to get coupled to any other net, because let's say you might have some other signals going here. If you don't want any coupling, one thing you can do is you can intentionally put two metals, like routings in the same metal layer, connect them to ground. This will ensure that I just have coupling to ground, that is increasing the capacitance to ground, but I'll be guaranteed that there is not going to be any coupling from this and this. Again, these are all simple tricks that you can do. And see, finally you do this, and then your layout is done. So this is one example layout. It's one of my old chips. So this is the entire portion, and what you see here, they are the paths wherein you give the input or take the output. Okay, so these are called IO paths or bond paths. And once you do the layout and get the chips fabricated, so you'll have the dies like this. So these are your, let's say, IO pads, something, and the spacing between these IO pads will be really small. I mean, less than 100 micrometers. So it's, in practice, it's difficult to feed any test signals directly. So what you do is you do something called packaging. That is, you take a big package which has pins like this with reasonable spacing, and then you go and connect all these guys like this. Basically, you bond a wire from the pad to this guy. So this process is called wire bonding. And I mean, of course, you can see that the material I am using for this wire should have a really small resistance, right? So what material do you think we'll be using for this? I want ultra low resistance. What material do you think has very low resistance? Gold. We use gold. Okay. Compared to copper, which has small resistance, right? I mean, here you don't want any resistance. See, now this wire, of course, has very small resistance, but any long wire will also have what? So you have a long wire, along with resistance, what else will it have? Something else? Inductance, right? I mean, any long connection is basically an inductor, right? So now, ideally, we expect that my input is here, and I was giving a voltage source. But that's not what's happening, right? Because here it goes to the IO pad. So there will be some capacitance with respect to ground at that pad. And then you have inductance due to this bond wire. So this is called bond wire inductance. And typically this is around 1 nanohenry per millimeter. So if you have 1 millimeter long of this connection, you have an inductance of 1 nanohenry. And in practice, this can range anywhere from 1 nanohenry to say 10 to 20 nanohenry also. So basically, even in your schematic simulation, you have to take into effect these guys and then simulate and make sure it works, right? Because then this will not. Okay. And see, let's say there are few tricks, some brute force ways. For example, let us say you find that from one particular net, say this net, I don't want a large bond wire inductance. One simple thing you can do is, this is that net, let us say. Instead of connecting it to only one IO pad, I'll connect it to say 3 pads like this. And then when I'm packaging, I'll have 3 of them like this. And finally, they'll be shorted when you are applying the signal, right? So now you see that I have inductance reduces by factor of 3, okay, because you have 3 of them in parallel. That is one way. But of course, then you are losing pads unnecessarily. Other thing you can do is, you can basically ask the packaging people to skew the position of the die so that here the bond wire inductance will be small. But of course, then you will have longer inductance in this. And I can show you some pictures maybe.
So in there we have to give design, like in packaging.
You have to take into account all these things when you are designing. That's what I'm trying to say. So this is basically the same layout I showed, packaged, fabricated and packaged. So I've opened the package here. So you can see all these guys, right? I don't know if you can see. So these are the bond wires. And here I've intentionally placed this die skewed to the left so that the bond wires here are small.
So your design.
Yeah. And this is, it depends. See, again, there are a few things you can do with respect to bond wire. See, another problem with bond wires is, we discussed during the differential signaling also. See, this is your supply and ground. Now from the supply also you'll have long bond wires, right? From ground also. And if this is, like taking switching currents, then we saw that the switching currents, when they flow through the inductor, they result in a huge voltage drop across the inductor, reduce the supply. And one of the fix was to put a large bypass cap. Okay, so this is something you can do again. And because of this, usually you separate the supplies for both analog and digital. You'll have separate analog VDD and digital VDD. So that way the switching currents will flow through the digital VDD. They will not come, let's say this is my digital VDD. You can have separate analog VDD. That will have this, let's say my analog block. So switching currents are flowing here, but they will not flow here. That way this supply is more clean. And in general, if you want to have a very clean VDD, you try to have a separate pin for it.
But normally we have only one VDD pin in a given.
Depends. I mean, in your op-amps, yes. But if you take mixed signal circuits like ADCs or PLLs, you'll have circuits which are consuming static power as well as switching power. So the blocks consuming static power, if you want them to be really good, you have to isolate.
Never saw that.
Yeah, because in op-amps and basic circuits, you are dealing with analog circuits, right? So there it's okay. But the moment you have mixed signal circuits, where you also have some switching currents, then you'll have to do this isolation also. Okay. Yeah. And I mean, of course, as you see now, this entire process of designing schematic layout and making sure after parasitics and packaging parasitics things work itself is an art. Okay. And yeah, so I can show you another picture. So this one other thing I have the IC also, I can show you. So yeah, you have to be you have to be really good at this, because see, as I mentioned, the final simulation, if you include all parasitics, that can run for several days, right? So that means you should have some qualitative understanding of what's happening in the circuit. Only then you can basically debug things quickly and do it. And that's exactly why I've been emphasizing on synthesizing and deriving circuits from scratch. See, one thing is to take a circuit and analyze it and see what's happening. That's a very good skill to have. But what will be even better is to see how the circuit could be derived from scratch. That will give a much better understanding. See, in fact, that might not be the way in which the circuit might have been derived in the first place. But if you reverse engineer and try to find out, you might come up with better ways and you can have better circuits. And especially in industry, the turnaround time to fabrication is really important, right? Because finally we'll be debugging, and if you don't have good understanding, you will take more time to debug. But if you have some good understanding of circuits, you can do the debugging process quickly, and the time to tape out also reduces, which is highly profitable for the industry. And that's exactly where skilled IC designers are needed, and they are in huge demand in the industry, and the industry pays you guys heavily. So that's where you guys hopefully will fulfill the demand, right? See, I don't know if you might be having some other interest, but the fact that you have taken the course means hopefully you have some interest in circuits, right? And you should actually be proud of yourselves to be at this stage, simply because if you have taken this course, which means you have taken the first level analog circuits course, 210 or 610 for PGs or UGs, and to have taken that course, you must have taken a basic circuit analysis course, KCL, KVL, Thevenin's theorem, blah blah blah, and signals and systems you should have taken. Only then you can understand frequency response, all this stuff. And to learn all this, you need to know calculus, which is what you studied in your school. So what I am getting at is, to reach this stage, if you have reached this stage, it means that you have had a successful training for the last few years in the right direction. And that's a really valuable skill, and you will be a valuable asset to a company. The reason why I am saying is, see, now you will see a lot of jobs and skills for which they say, hey, you train for 2-3 months or 4 months, you will be good at it. You will see a lot of online courses saying, hey, you do this course for 3 months, you will be a master at this skill, and then you can get jobs. It is partially true, we have some decent paying jobs there, but the barrier to entry for those jobs is really low. So you should remember that if you can learn that skill in 3-4 months and be a master at it, there will be lakhs and lakhs of people also in the same level. So which means for a company, that is not adding any value, right? Exactly, because they know if not for you, there are like lakhs of people waiting. Okay, but that is not the case with fields like circuit design, where the barrier to entry is high, and you guys have already crossed that barrier. Okay, and finally what I'm saying is, in the future when you are steering your career, make sure you specialize in something where the barrier to entry is not really low. Only then you will not be replaceable. And of course, make sure that that field has enough number of high-paying jobs. That is also important, right? If there is no employment opportunities, then learning a skill, even how niche it is, it's not profitable for you, right? And of course, circuit design is one such field where the barrier to entry is high, and you have a lot of high-paying jobs. That's why you don't see online courses saying, hey, do this course for 3 months and then, okay. And for industry, that's also important because, see, as you know, this entire fabrication business is very costly, chip fabrication. Even in academic setting, for us to tape out some 20-30 chips, that can cost all the way from 6 lakhs to 10 lakhs, and a very old process. If you go to 14 nanometer 28, it will be crazy.
Sure, that's like 60 lakhs or something.
Depends. If it's 14 nanometer, it will be very costly.
Yeah.
Okay. So for the industry, it will be even more costly, right? So basically, you can't make mistakes in this. If you make a mistake, it's gone. It's not like making circuits on breadboard or PCB. Like I put the 2K resistor, I put it and put 1K resistor, right? So that is why you guys are in demand. So now, see, I'm not saying anything against taking jobs which are having low barriers of entry. It is also good, but you guys are the best of the students in the country from IITK. So you shouldn't settle for something low, right? Aim for better things. So that's about it. I'll stop the thing.